Okay, this is part 2 of lecture 14. We're talking about acid-base reactions, and this is going to focus on the equilibrium reactions of weak acids and bases. So first I'm going to show you that toolbox page again, which is just so critically important. And this is in Canvas under module 8. What am I trying to do here? I'm going to pop this out. You go to module 8, and it's called Toolbox Acid Base. And if you can print it out, that's great, but otherwise put it somewhere where you can refer to it frequently. This table is, it shows you these strong acids, the big 6 you need to know. And then the ones in the middle, these are your weak acids. Over here are your weak bases. The bases get stronger as you go down because these are the conjugates. All right, here's an acid, here's its conjugate base. Or here's a base, is a conjugate acid. What you call it, a conjugate or just the regular, depends on what the reaction is. If the reaction is involving this and that's a product, then this is the base, that's the conjugate acid. But if the reaction is with this, and this is a product, then this is your acid and your conjugate base. So whatever is in the product is called the conjugate. When you have the strong base, or mostly what we're going to work with is strong acids, your reaction goes to completion. It's a single arrow. It goes 100%. At the end of the reaction, it's very quick. You only have products left. You have none of the initial acid left. All right, it's completely reacted with water to give you hydronium ion and the base, the conjugate base of the acid. If you have a weak acid, it only goes a little bit forward. Most of it stays as reactants. Most of the acid will stay as the acid form. Only a small percentage goes to the conjugate base. So we show that with the double arrow. So anytime you have a reaction with the weak acid, use the double arrow. When is it weak? If it's not one of the big 6, excuse me. If it is not one of the big 6, you consider it as weak. So you have to memorize the big 6. Chlorine, bromine, iodine are halogens right on top of each other. So the acids of those are strong. Perchlorate, sulfate, nitrate. So know those 6 are strong acids. And this is in the Canvas. Okay, let's go to slides. Right here. And this is 8B, acid-base theory. It's the slide set that I was using yesterday and today. All right, let's go up here. So your strong acids and bases react 100%. They produce a high concentration of ions, right? Because the entire acid has reacted with water to create an ion. So it's a strong electrolyte, which means it's a strong conductor of electricity. You have a single arrow because it goes to completion. A weak acid or weak base only reacts partially, so you have a double arrow. It's a weak electrolyte and therefore a weak conductor because it only makes a very small percentage of it becomes ions. So just a small amount of ion, small concentration of ions are made. And so you have an equilibrium, which we show with a double arrow. So if you see a single arrow reaction, you know that at the end of the reaction, there's nothing left on the left side. And obviously, we're going to have water, but of the core reactant, the acid, it's all product. If you see a double arrow, you have some of each. And in the case of that double arrow is with a weak acid or a weak base, most of what you have is still the reactant. Only a small amount becomes product because as soon as you have, as this builds up, since this is a weak acid, it's a stronger base. So as soon as, so you have a fairly strong acid and stronger base, So as soon as you have high enough concentration of these, they start to run into each other, and they also react, and they make this as a product. So it goes this way, and then it goes this way. At a certain point, so this is called the reaction rate, forward and in reverse. At a certain point, you're going to hit equilibrium. At equilibrium, the rate forward equals the rate backwards. For every one that goes forward, one goes backwards. What that means that your concentration of each of these, not water, but each of these at equilibrium becomes steady state, becomes constant. So whatever that number is, it's not equal, it's constant. So whatever that concentration is, and that concentration is, and that concentration is, doesn't change, because for every one of hydrofluoric acid that becomes, conjugate base, let's say, the conjugate base is making the hydrofluoric acid. So the concentration doesn't change the same, and your rate becomes equal. So make sure you don't get those two terms confused, the rate and the concentration. One is equal, one's constant or steady state. So this is a visual pictorial example of what's happening at equilibrium. We have dinitrogen tetroxide, and I'm just going to call it N2O4, it's quicker. Initially, this is pure. You put some in a container, and that's the only thing left. But they can decompose. So it starts decomposing into nitrogen dioxide. And notice there's no charge here, so this is not a polyatomic anion. This is nitrogen dioxide. So you see some of the nitrogen dioxide molecules start to build up in concentration, right? Started out just a little, you get more and more. Pretty soon you have enough of these nitrogen dioxides in there that they can start running into each other. And when they do, they form N2O4. So equilibrium, and notice the color change from the production of nitrogen dioxide. So that's a visual observation of a reaction happening. You have a color change. So at equilibrium, you have a set amount of nitrogen dioxide molecules and N2O4 molecules. Because whenever you increase the nitrogen dioxide, they run into each other more frequently, and they go back and they create the original product. So this is equilibrium. And it will stay this way forever. If nothing else has changed, it will stay that way forever. So this graph is very important, showing the two aspects of equilibrium. And this is what we just looked at. At the beginning, let's look at the rate. The rate of the forward reaction starts at very high, starts to get slower because now you have a competing rate of it going backwards. And that increases quickly, right? The more product you make, the more you can have that reverse reaction. So the rate of the reverse is increasing because it starts at 0, and the forward is decreasing slightly because there's competitive reactions going on. And at equilibrium, they both hit a plateau. They have the same rate, because when you hit equilibrium, every time one goes forward, one goes backwards. So the rate is equal. The forward and reverse become equal. Your concentration, at the beginning, you had no nitrogen dioxide. You had only pure N2O4. So as this decomposes, the concentration decreases, right? And as it decreases, your nitrogen dioxide, your product, increases. When you hit equilibrium, so at this point, this is the same time point, again, you have a plateau of your concentration amount. It stays fixed. So yes, the rate also stays fixed. But what's important is your forward and reverse reactions are the same. Here, your concentrations are not the same, but they are both set. They are both fixed. They do not change once equilibrium is hit. So these are very important aspects to understand and remember about what equilibrium is. So when we have a strong electrolyte, so in this case, we're talking about a strong acid. So this is your hydrochloric acid, you know, your hydrobromic acid, hydroiodic acid, etc. That's your single arrow. And remember, water is in this reaction, molecular ionization, because it's actually reacting with your acid. It's a chemical reaction going on here. Single arrow means this is 100% to completion, 100% ionization. All of your acid becomes ionized. At the end of the reaction, you have no starting acid left. You only have the ions that were produced, the conjugate base and then the conjugate acid of water. So you have water molecules, you have hydronium ions, and you have the conjugate base. You have 0 starting acid with a strong acid, strong electrolyte, single arrow. So your inventory is, and it's what this picture shows, your inventory is just the product. And again, I don't need water in the test, but Alex asked for water. So when you're asked for the inventory, you only have a major inventory. You have no minor. You don't have a minor inventory when you have a single arrow. And so these are strong electrolytes. They produce lots and lots of ions, which can carry a current. And these are your big 6 that you have to know. On the other hand, a weak electrolyte is just the opposite. Here's your starting material again, but this time it's weak. You have the double arrow because when you get sufficient product made, these are strong enough as acids and bases to react themselves and create this as a product. So you get partial ionization, only a little bit of this becomes ionized. And at the end of the reaction, see, most of your material in your beaker is still what you started with. It's still your starting acid. A little bit has been ionized. And so you have a little bit here. So your inventory is major. It's just what this picture shows. This is your major, this is your minor, right? What's mostly there, that's called our major. What's a little bit there, that's our minor. So when you have a double arrow, the major is your reactant. Your minor is the product. It's that simple, okay? So we call this, these are poor conductors. They are weak electrolytes because they make very little ions. This is acetic acid. It's only 1% ionized, which means at the end of the reaction, 99% of it will be in the acid form and 1% will be in the conjugate base form. So that's not very much. It does happen. It's measurable, but it's pretty weak. So this is a weak acid. Only 1% of it at the end of equilibrium becomes ionized because of the reverse reaction. Your major is going to be your acetic acid. Your minor is the acetate ion and the hydronium ion. Some other examples with cyanic acid, 0.001% ionized, but you can still measure this. So this is still called a weak acid, but you can imagine your inventory, it's almost all this, and then your minor would be this. Hydrogen fluoride, the most common, one of the most common ones you're going to get in examples, it's 7% ionized. So that's actually pretty decent for a weak acid, but it's still not 100%, is it? So at the end of the reaction, 93% of what's in your beaker is going to be in the HF form. This actually shouldn't say aqueous. And 7% will be hydronium and the conjugate base, fluoride ion. So major, minor, because of the double arrow. A weak base, ammonia, same thing though. 99% of it is in the ammonia form when it reacts with water. 1% is ammonium ion and hydroxide. So your inventory on this one is major and minor. When you have the double arrow, that's your key. And why do you have a double arrow? Because it's weak and it's not going to 100%. At a certain point, the products are reacting with each other and making the starting material, the reactants. So that's what we call our inventory. Your major and your minor, and the only time you have minor is when you have a double arrow. I have a single arrow, I do not have minor. I only have the major, which is the products. It's a real cut and dry rule. When I have double, most of my material is still in the original form. So that's my major and that's my minor. Okay. There's something called extensive reaction because we say it goes, you saw the 7% for the hydrofluoric acid and the 1% for the acetic acid. So those are all obviously to a small extent. There are situations where you can have a weak acid or base, but it still produces, actually more of it goes to the product side. It's still called a weak. We're not really going to work with those. Just be aware that it happens. So that's called a large extent. Over half of it reacts. At equilibrium, you actually have more on the product side than the reactants. But we are working with small extent weak acids. So our examples are going to be the large extent, which is 100% single arrow, and our weak acids are small extent, double arrow, and they're going to be less than 50%. So just something to be aware of. So our electrolytes, which conduct electricity because they create ions. If you do not create ions, you do not conduct electricity. Sugar dissolved in water does not conduct electricity because it does not create ions. It's molecular dissolution. Dissolves, but it still stays as an intact sugar molecule. No ions, therefore no conductivity. If it just produces a little bit of ions, it's a weak electrolyte and it produces a weak current. It carries a weak current. So our soluble ionic compounds are strong electrolytes because they completely dissociate into their constituent ions. Strong acids and strong bases because they react with water to create it's completely ionized. Weak electrolytes, we're not dealing with weakly soluble ionic compounds, but if you do, they just dissolve a little bit. So the same weak acids, weak bases, all three of these, they only make a little bit of ion. So it does carry current, but not very strong. And then non-electrolyte, of course, is your insoluble ionic compounds. If it's an ionic compound, but it doesn't dissolve, like magnesium carbonate or calcium carbonate, it's obviously non-electrolyte because there's nothing going on. And molecular compounds that are not acids and bases like sugar and ethanol. They dissolve, but they do not create ions. So your strong electrolyte, you get a single arrow because it's a complete reaction. Your weak acids and bases, we write with a double arrow. And for insoluble, you say no reaction. And the molecular dissolution, of course, it's a single arrow, but you're simply changing the state of your sugar or your ethanol from its original to the aqueous form. I'm going to pause just for a moment. Okay, there's one other aspect about acid-base chemistry that we use called a titration. And I'm going to work through a couple of those problems. And you'll be doing this lab in the fall. It's actually a really fun lab. Up to now, I've been talking about acid-base chemistry in water, making the acid. Once you have your solutions of acid bases, you can use them and the stoichiometry to calculate the concentration of an unknown concentration of an acid or a base. We call that titration. So let's go to the slides. Like I said, you will be doing this in the fall. So titration is we use a burette, and you have your unknown in your beaker or your flask or Lemire flask. You know what's in the burette. You know the concentration. You know the identity. You know the identity of what's in your unknown concentration. You have to know the acid because you have to know this reaction, because you know you need to have the mole-to-mole relationship between this base, in this case we're going to use a base, and this acid. With that, you're going to hit an equilibrium point, which I'll explain. You're going to have recorded the volume that you used. What you're doing is you're completely neutralizing this acid with the base, right? An acid and a base, if it's not water, a pure acid and pure base make water. It's called a neutralization reaction. Let me see if I can find an example of one. So here, these are not water. So this is an acid-base reaction, but it's not involving water. I mean, they're in water, right? You've made them in water. So the initial water reaction has already happened. So you have an acid and you have a strong base. And when you mix them together, they're going to react. This base is going to steal the protons of this acid. That doesn't change. The acid-base behavior does not change. And at the end, when it's completely done, so here we're not writing stepwise because we're looking at the whole reaction. At the very end of all the processes, you have no more acid left, and your H and your OH have formed water. So in a neutralization reaction, you get water as a product when you have a non-water acid and a non-water base. Do you see that? This is oxalic acid and sodium hydroxide. It's the hydroxide part, that's the base. The sodium is just there as a, to pair it, to balance out the proton, the negative charge rather. So we use the stoichiometry of this, I'm gonna work through a couple of these, to calculate when you know how much hydroxide you used to neutralize this, then you can calculate the concentration. So when you have a titration, there are things you have to know. You've got to know the titrant is what's in the burette. The titrant is here and you know everything about that. You know the identity, you know the concentration. You have to know the identity of the acid, which in this case is what our analyte is, our unknown, because you have to know the chemical reaction that occurs and the mole-to-mole relationship between your acid and your base. So what we're using is the known concentration of one solution to determine the unknown concentration of another. And it works because the acid-base reactions, they neutralize each other. For this to work, you have to, like I said, you have to know the reaction. It must be rapid and complete. It's got to happen immediately. You're actually watching for a color change because you have an indicator in there. And then you're going to determine the exact quantity, and the more precise you are, the better your result of the one reactant, which is the titrant. It's what we're adding. And then you're going to use stoichiometry to determine the concentration of your acid. A burette is read backwards. So you start, you fill it. When you're ready to go, you read your starting volume, you write it down. When you're finished, you read your ending volume, you write it down, and then you subtract the ending volume, because notice that number is going to be bigger, minus the starting volume, and that tells you the amount that you used. So you record both numbers, and then your ending minus your starting, and that tells you the exact volume that you used. Okay, so this is our setup. The equivalence point is a point at which, when you're adding your base to your acid, the base is taking the protons from the acid, right? So you add OH. Let's go to the whiteboard. So this is we'll just draw a beaker. Right, my wonderful art, modern art. And you have a burette with your titrant. That's got, we're going to analyze an acid, and so this is a base. And it doesn't matter if it's sodium hydroxide, potassium hydroxide, what really matters is the OH. And this is full of acid. So every time you add OH, it's going to react with the acid, the proton, right? It's going to steal a proton from the acid. And so you end up with HOH, you end up with water. So for every mole of OH you adding, hydroxide ion, you're stealing a proton from the acid and you end up with water. Okay, this keeps going, it keeps going. You're swirling this, by the way. As you add this, you're swirling it, so you're continuously mixing it. So everything comes in contact with each other. At some point, you have no more, every acid is paired, the protons. Every proton has been taken by a hydroxide. You see that? At some point, you've hit the equivalence point. All of the acid protons have been taken by the OH. So what happens at that point? So I'm going to erase my little. So every green acid available proton has been, sorry, I have my colors backwards, but every proton's been taken by the hydroxide. So what happens if I now add some more hydroxide? There is no more acid for it to react with. All of the protons have been taken. So you now have excess hydroxide, right? You have hydroxide floating around in there. You have put an indicator in your acid that will chemically react with the hydroxide. And in this case, for the experiment we're going to do, it will turn pink. So the indicator plus the OH ion turns pink. It's not happening while you still have acid in there, because the acid reaction is going to happen more faster. And sometimes you'll see a little pink show up, but you swirl it and it goes away because the hydroxide is being consumed or is consuming the acid, however you want to think of it. As soon as you have even the tiniest bit of leftover hydroxide, there's no more acid for it to react with. So now the indicator is like, all right, my turn. And it reacts with it and you get a color, because that's the product. You will see that pink color. You stop. When you see the color, you stop. That is your equivalence point. See, in this case, it's blue. That depends on the indicator that you use, the color that you get. So at the equivalence point, you've equally, your hydroxide and the acid are equally matched. And as soon as you see the color, because you have that tiniest little bit of extra hydroxide, that's your endpoint. That's when you stop. That's when you write down your ending volume. You subtract your ending minus the beginning volume, your numbers. That volume that you used, you are going to now use with the stoichiometry to calculate your unknown concentration. So endpoint and equivalence point. Equivalence point is when the moles of hydroxide are equal to the moles of protons available. And then the endpoint is like when you stop the reaction. It's pretty much the same thing. They're just slightly different meanings. So now we're going to calculate. We're going to use this to calculate our unknown concentration of our known acid. This is just a little aside because we're using milliliters here. When you're doing our moles or molar, if you want to use milliliter, if you use the milli times the top and the bottom, let me go back to the board a minute, see if I can say this where it makes sense. But if it's confusing, don't do this. So the slide gives the example of 2.03 molar solution. That equals 2.83 moles of solute over 1 liter of solution, right? But what if I'm trying to find it and I have milliliters hidden here? Well, this is the same as saying 2.83 millimole over 1 milliliter. If your milli is top and bottom, it's the same thing as saying 2.83 moles over 1 liter times 10 to the minus 3, which is a millimole, over 10 to the minus 3 mole. That's a millimole. So you're basically multiplying this because 2.83 moles times 10 to the minus 3 is millimole. As long as you do the same to the top and the bottom, this is equal to 1. Right? Top and bottom are identical. So you're multiplying this times 1. So that's why you can do this. So as long as you do the same unit change, top and bottom, it's the same thing as multiplying it times 1, and it's just a convenient way to use milliliters. You're going to get an answer in millimoles. You're not going to get an, so be consistent. It's just if you're comfortable with it or you're comfortable enough with the math, this can be done because it's done in the example. But like I said, if you find it confusing, then you're better off with just go ahead and convert to liters and work the problem from there. So here's the example. This is a titration example. 25, and notice, don't forget your sig figs there, 25.00 moles of oxalic acid. You have to know the formula because you have to write the equation. You have to have a balanced equation because you have to have the ratio of base to acid or hydroxide to protons. It's titrated with, there's your concentration of your titrant, your base is in your burette. There's the volume that you used. You wrote down your beginning volume, you wrote down your end. The end minus the beginning equaled 37.5 mils. So what's the molarity of your acid? What's your concentration of your acid? So there's the equation and we're going to solve it. So let's go to the whiteboard. Just like everything else, if you go through the same steps every time, it will work every time. Again, I'm going to eliminate the phases just because of space issues. And I started too far over. Let me do this again. This is a single arrow because you can only use strong, that's a very strong base. Strong acids are base in this reaction, in a titration reaction. You cannot use something that's going to do equilibrium. It has to be complete and it has to be fast. Water is your product of a neutralization reaction. And these two are neutralizing each other and they end up with water. Because what's really happening, your active base is this. So if OH is stealing a proton, you get water. Do you see that? So that's why water is a product, and that's why it's called a neutralization reaction. So that's what's happening with my acid and my base. I have two, this is polyprotic. I have 2 protons available for every mole of acid. I have 2 moles of protons that can be taken. So I will need 2 moles of base for every 1 mole of acid because it has 2 hydrogens there. It has 2 protons that can be removed. All right, so now we have our relationship. What are, let's see, our data. Our acid is 25.0. You have to know that as well. How much did you use? I neutralized it with 37.5 mils of 0.500 molar base. So I write my numbers underneath the formula of each. So we're looking for the concentration. Too many pens. Now I'm going to use the, I'm not going to convert the millimoles, the milliliters. I'm going to use the way the slide uses it, which refers back to what I was talking about of as long as you keep the same unit top and bottom, then you can do that. In other words, 0.500 mole of sodium hydroxide is equal to 0.500 moles over liter, right? But this is also equal to, if I just change, put milli both top and bottom, it's also equal to 0.500 millimoles over 1 milliliter. As long as I'm consistent with my unit change top and bottom, it does not change the value of the concentration or the definition. So I'm going to use that because it's just a quicker way of doing it. Otherwise, all you do is you simply just convert your mils into liters as you're working through this problem. Okay. So first of all, here's our volume and here's our concentration. I need to know my moles, or in this case it could be millimoles, that I used up. Remember, molarity is moles over volume. Volume is in liters. So then my moles equals molarity times volume. My molarity is 0.500. My volume is 37.5. I can do this if I call this millimoles. Because it's moles over liter or millimoles over milliliters. So when I multiply, and I'm going to rewrite this now a little neater. So my millimoles is going to be equal to mole times the volume, 0.500, and I will put my units in here. That's the unit for the moles. And here's my volume. See, if you do that, your volume cancels out. I have millimole top and bottom, so I can do that. And then I end up with 18.75 millimoles, okay? That's our unit that we kept of sodium hydroxide. Now, this is 3 sig figs, this is 3 sig figs, but I don't want to cut off my numbers yet. I'm not done calculating. I like to keep more numbers. I'm not going to round yet. So draw a line under the number that lets me know the 7 is my significant digit, because this is 3 sig figs. So I can keep using this number, but put a line under the 7 to remind you, oh, it's not 4 sig figs, it's 3. So now I know that 18.75 millimoles of sodium hydroxide were consumed. Okay. I want to know how many millimoles of acid were consumed, because ultimately we're looking for the molarity of acid, which is going to be millimoles over milliliter. So I'm going to take this number so I have my millimoles. So let's find the acid now. And that's through the stoichiometry. If I use, this goes right back to all of the equations we've been doing. If I used 18.75 millimoles of this reactant, how much of that reactant did I consume? Just like your limiting reagent. Instead of putting moles on the bottom, we're putting millimoles. Again, if that's just uncomfortable, you can convert to liter, and then we're still in moles. And as long as you're consistent with the milli, this works. How many millimoles of oxalic acid did I consume? I get this number from my equation. For every 2 millimoles of hydroxide, I had 1 millimole of oxalic acid. My sodium hydroxide will cancel out. I divide 18.75 divided by 2, and I get 9.375 millimoles of oxalic acid. Again, underline my 7, because to let me know I'm still only have 3 sig figs, but I don't want to drop numbers yet because it makes a difference in my final numbers. So I used 9.375 millimoles when I used 18.75 millimoles of hydroxide to consume 9.375 millimoles of acid. Well, I now know, and that is how many millimoles of acid were in that beaker. Because as soon as they were all consumed, I got a pink color and I stopped. So this number is the amount of millimoles of acid that were in that beaker. That's what you just figured out by working backward. Well, now I have a volume, I have number of moles or millimoles, I can calculate my concentration. So I'm going to erase this. So it's kind of an equation in reverse. So my molarity of my acid is millimoles over milliliter. And remember, that is the same as moles over liter. You just cancel out the milli top and bottom, and you get moles over liter. It's the same thing as saying 10 to the minus 3 moles over 10 to the minus 3 liter. That is the same thing. And if I cancel out my 10 to the minus 3 top and bottom, I have moles over liter. So that's why this is going to work. So I'll go up here to the numbers that I have. What do I have? I calculated that I consumed all of the acid in that beaker, and it was 9.375 millimoles. I've underlined the 7 to let me know there's 3 sig figs. And my volume was 25.00 milliliters. This is equivalent to mole over liter because I can cancel my milli out. So when I do the math, 9.375 divided by 25, and I remember that my answer has to be in 3 sig figs. My acid concentration, if I would write it correctly, is 0.375 molar. So we use titration to determine the concentration, the unknown concentration of a known acid or base with the acid-base relationship and our stoichiometry. Just like your combustion, just like everything else you've been working on, once you know the amount of one you have, you can calculate the amount of the other that was used. In this case, we need the additional step of a volume because we're doing molarity, and we're given that at the beginning of the equation because that's how you set up the experiment. Okay, we're gonna do one more. This is the next slide. And it says a 25 mil sample of nitric acid is titrated with 75 mils of a 1.30 molar calcium hydroxide. And I'm going to write this down. What's the concentration of the nitric acid? So your nitric acid is in the beaker. Your calcium hydroxide is in your burette. The calcium doesn't really matter because it's the hydroxide that's doing the action. So our reaction equation is, again, I'm not writing the phases just because of space issues. Now this time, calcium hydroxide, this is calcium hydroxide. So I have 2 moles of calcium of hydroxide. So I have to put a coefficient to balance this in front of my 2 nitric acid. So this time it's actually 2 moles of acid are consumed for every 1 mole of hydroxide added. Okay, neutralization reaction. What's really happening is this proton's going to the OH. You're getting H2O formed because it's not a water acid or base. These are non-water acids and bases. You produce water. Okay. So what are we starting with? We are starting with, according to this, the volume of this, because you have to know that when you set this up, it's 25 mils. When you took your beginning and your end volumes of your calcium hydroxide in your burette, as soon as you saw the color change, you stopped, you subtracted the beginning from the final, and you found out that you added 75 mils, 75.00. You know your concentration of the base that you added. You have to know that is 1.30 molar. So you're just trying to find this concentration. To do that, you need the number of moles. So let's find out how many moles of base that we used. So again, you had, moles or millimoles, I'm going to use this again because I have milliliters, equals concentration times volume. And if I write my molarity as millimole over milliliter, which is perfectly acceptable, and my volume is going to be milliliter, my milliliters will cancel out and give me millimole. So I'm going to do that. So my molarity is 1.30, and instead of writing a capital M, which is what this is, I will write millimoles over milliliter. That's the unit. And my volume was 75.00. 0.00 mils. I cancel those out. Now you can do this in one step, because this is going to give me millimoles of calcium hydroxide. You can keep going with the relationship, the stoichiometric relationship, because now we have millimoles of calcium hydroxide. And now we want to say, well, all right, how many millimoles of acid did we use? And we go to our equation and you say for every 1 millimole of calcium hydroxide, I use 2 millimoles of nitric acid. My millimoles of calcium hydroxide will cancel out. See, I'm continuing to cancel out my units and I still am down to millimoles of acid left. So if I do that, and say 1.30 times 75 times 2 times equals, what's going on? Okay, my computer calculator froze, so hopefully this is correct. If not, I'll double check it. In fact, I am going to double check it. Okay, 195 millimoles were consumed. Well, now I can find the concentration because I need the moles of solute, or the moles of, in this case, the acid used, divided by the volume, and I have both of those. And again, as long as you have milli in the top and the bottom, you can do this. I have 195 millimoles. And I have 25.00 milliliters. We are doing 3 sig figs because this was given to us in 3, and so that would set the number of sig figs. So I get 7.8, but it's got to be 3 sig figs, so it's 0. And that is the concentration, the unknown concentration of our acid. And if we go to that slide, because it's worked out, so you can practice this. Okay, here's the first one I did. The second one, you have this blue line. As long as you're not in the presentation mode, you can move the blue line. You can try to work this out in one step. You can work it out, break it up into the steps. The answer is 7.80 molar. So that's how we do a titration. Like I said, you're likely to get some questions on it next test, exam 4. But it's a very common, very, very important reaction. But you just take the steps, think it through, take the steps. It's really no different than our combustion reactions and these other things we're talking about. You have a certain amount of one, how much of the other is consumed or produced. It's just you have that extra step of determining the moles or millimoles of your base, of your titrant. That's really the only difference. Everything else is the same. And of course, we're not talking about a combustion reaction. We're talking about an acid-base reaction. Very special, very important, very critical reaction. Again, you can make a lifetime study of it. It's a part of everything. Absolutely, I can't think of much of anything that does not involve acid-base reactions. All right, so really that's the end of the lecture 14 recordings. All right, you guys have a good weekend.